Okay, hello guys, welcome to the first day of the F equals MA physics competition daily practice. So just since today is going to be the first section, we are going to briefly talk about what this physics competition is. So basically F equals MA is the most famous physics competition in the United States. So it's only accessible for the students in the US, so you don't have to worry about, like, say, competing with other students across the other nations. So it's going to be the best physics competition you will attend in high school. So for this competition here, you will only be tested with mechanics, so like kinematics, dynamics. Those will be the focus from this competitions. So in this 10 days of daily practice, we are also going to go through some of the most basic problems from the test, so that you have some better knowledge on what this test is about, to see whether you are interested or you want to maybe study or compete in the future. It's going to be a very fun exam, because you will see a lot of problems that are not very, like, say, tedious. They are also often just related with your daily life, so it's going to be a pretty good way to see the practice problems. Okay, so the problems we choose for this daily practice, first of all, are mostly from the previous past papers, so all the way dated from 2011 to 2019. And also for the problems, we also chose those don't require a lot of math in the problems, because some of the problems are very math heavy and you need to have like some pre-calculus or algebra 2 knowledge to solve the problems. But just for the daily practice, we will just get a sense on those problems, so the math wouldn't be that crazy. And also for the physics knowledge, if you have some basic like grade 8 physical science knowledge, then that should also be good. Okay, alright, so that will be all on the introduction, and without further ado, let's take a look on today's daily practice, which is on the displacement, velocity, and acceleration. So this will be the three things that you learned at first for almost all the physics courses, I would say, and also will be the basic foundations on kinematics. So let's first review some of the basic concepts on this part. So what is a displacement? So keep in mind that displacement is different from the distance, right? When we say the distance, we only measure the distance between the 2 points, right? We call this the distance. However, for displacement, it must has a direction. So suppose if I go from place A to place B, the direction is going to be to the right. However, if I want to go from place B to place A, you can see that now the direction will be to the opposite side. So in displacement, you always need to know that we have to care about the direction and also the magnitude. So this will be the two things that you want to pay attention to. Okay, all right. And then if you want to just calculate the displacement, you will need to know the positions. So suppose it would be better know from a number line. So suppose we have a number line, and then we have the point 0, we have the 1, we have the 2, and also -1, -2, and so on. Suppose you have a point A on -1, and then you go all the way to the point 2 here, which will be the point B. In this case, you can see that the direction will be to the right, and the displacement is just going to be a 2 minus -1 equals 3. So you can see that we use the final position minus the initial position to calculate the displacement. Okay, all right. And then what about velocity? Just similar to the displacement, velocity also has a direction and a magnitude. So it's going to be a little bit different from the concept of the speed. It also has the magnitude and the direction. So basically, velocity measures how fast an object changes its positions. Like, say, if you want to go from place A to place B from the previous example, you can go from A to B, like, say, in 3 seconds, right? But you can also go from A to B in only 1 second. So you can see that the second case is a lot faster than the first case. So to calculate velocity, we have to also know the duration of the movement, right? Or just like the total time you spend in this trip. So we just take the total displacement divided by the total time interval to calculate the velocity. So for example, if I want to go from A to B, the displacement as we calculated is going to be 3 meters per se. And if we spend in total 3 seconds to go from A to B, then the velocity is going to be a 3 divided by 3. So 3 meters divided by 3 seconds equals 1 meter per second. All right, this is going to be how we calculate the velocity. And then lastly, we also have the notion of the acceleration, because in physics, sometimes, especially when we have forces, the object is going to have different velocity, right? So if we have different velocity at different time intervals, we will have acceleration. So to calculate the acceleration, we also want to measure how fast the velocity is changing. So we are going to take the change in velocity divided by the time interval. So this is the way to calculate the acceleration. All right, so this will be all of the basic concepts. So just to summarize, the displacement tells you the change in position, and the velocity tells you how fast the object is changing its position, and lastly, the acceleration tells you how fast the object is changing its velocity. Okay. All right. So if we want to do some calculations, I mean just like the basic stuff on the calculations, this will be the 3 kinematic equations you have to know about. Okay. But we can also derive this from all these definitions. So for the first one, it's telling us that the final velocity equals the initial velocity plus the acceleration multiplied by the time. So this is actually a variation from the acceleration formula, because we know the acceleration is equal to the final velocity minus the initial velocity. This is to calculate the change in velocity, right? And we divide it by time. And then if you just like multiply both sides by the time and then isolate the final velocity, you are going to have the final velocity equals the initial velocity plus a multiplied by the time. And that's it. So this will be the way to calculate the final velocity if you know the initial velocity and you know the acceleration and also the time. And oftentimes if you have just like a 0 initial velocity, just replace that with a 0 will be good. Okay. All right, and then after that, we also have a few other kinematic equations. The second one is a way to calculate the speed. All right, so to calculate the speed here, this will also be applied to only like a linear motion, and we also have a constant acceleration. So this is just telling us that if we have like the speed is changing, then the total displacement, the delta x, is going to be the average velocity multiplied by the time, which makes sense. If you have the velocity changing at a constant rate, then you just calculate the average velocity, right? That's going to be the velocity for the entire trip, and then you multiply by the time. And then the average velocity in this case is just calculated as the final velocity added by the initial velocity divided by 2 and then multiplied by the time. So this will be how you can understand the second formula. And then for the last formula, even though it looks very complicated, however, if you combine the first and the second, you will get the third. So to get the third equation, all you have to do is to substitute this final velocity over here by the first equation. So we know that it's going to be the final velocity added with the initial velocity divided by 2 multiplied by the time. And we also know that the final velocity is just equal to the initial velocity added by the acceleration multiplied by the time and then added by the initial velocity divided by 2 and multiplied by time. And then if you just like combine the like terms like the initial velocity, you will just get the initial velocity multiplied by time plus 1/2 times the a times the t squared. All right, so this will be all, yeah, sorry about that. This will be all the algebras with all the kinematic equations. So I know we have done a lot of algebras here, and we have a lot of variables. And if you first learn these equations, you might think that, okay, those equations are really weird and they don't make any sense. But trust me, as you dive into the details of kinematics, especially when you have the chance to look at the graph of the kinematic equations, all of this will make a lot of sense. Okay, we will go through some of the kinematic graphs in the third day, so stay tuned to that daily practice. All right, and now let's try a few practice and see how we can solve them. For the first one, suppose we have a cyclist travels at a constant speed of 22 kilometers per hour, except for a 20-minute stop. The cyclist's average speed was 17.5 kilometers per hour. And how far did the cyclist travel? Okay, so this one is actually the very first problem in the 2011 F equals MA problems. So this could be the easiest F equals MA problems in the last decade, I would say. Yeah, so let's take a look on this one here. So basically, we know two velocity or two speed. The first one is the 22 kilometers per hour. This will be the actual speed when the cyclist is traveling, but there is a 20-minute stop. And then the cyclist's average speed was 17.5. So you can see that this speed is actually slower than the previous one because it's the average speed, right? It's dragged down by the 20-minute stop. So in this case, we want to know how far did the cyclist travel. So to solve this problem here, the best way is to assume the time. So if we can assume the total time is equal to, let's say that it will be t. So in this case, we can actually set up an equation, right? Because if the total time is equal to t, then the total distance is going to be a 17.5 multiplied by the time, right? This is going to be the total displacement or distance. But then if we use the other approach, we also have a 22 kilometers per hour. But in this case, we are not going to travel the whole time, right? We only travel by t minus 20 meters. And here it will be best if we assume the units will be hours. Just to simplify this a little bit. So if we have a 20-minute stop, it's going to be t minus a 1/3. Right? So this is going to be our equation here. So now we just need to solve this equation here so we can move some stuff here, 22 over 3, and then it's equal to, this will be a 4.5 multiplied by t. And then we can solve this here to find the value of the t. And remember, you can bring a calculator. So if you have to use a calculator for the practice here, just go ahead. You can use a calculator for sure. Okay, so if we do the calculation, okay, so for this one here, you will get the time to be roughly about 1.629 or 1.63 hours. Okay, and once you got this here, you just need to multiply this guy here by the 17.5, which will be the speed, and that's going to be 28.52 kilometers. And now you can see that the closest answer is going to be the answer choice A, and here you have the answers. All right, yeah, so this will be the first one here, so seems not too bad, right? So I'm sure that if you've seen this problem, like say in some math competitions, even like MC10, MC12, MC8 even, I think you will not be surprised. So this will be how the problems are like from the F equals MA, probably the easiest problem you will see. Okay, so that will be it for the first one here. And now let's check out the second problem. So how should we deal with the second one? For the second one here, we consider a dripping faucet, where the faucet is 10 centimeters above the sink, and the time between drops is such that when one drop hits the sink, one is in the air and the other one is about to drop. So at what height above the sink will the drop in the air be right as a drop hits the sink? Okay, so for this problem here, it's the problem one from the next year, 2012. So here it would be great if we can draw something out. And to be honest, I'm really bad at drawing in general, so let me just try my best. Okay, so here we have a dripping faucet, and let's say that we have the sink to be over here. So now we will have the drops. So when one drop hits the sink, so we will have one drop just over here, just hit the sink. The other one is going to be in the air. We are not sure where the drop is in the air. Let me just draw the drop over here, and the other one is about to drop. Alright, so we now want to know what height above the sink will the drop in the air be right as a drop hits the sink. Okay, so how do we understand this problem here? So you can see that we know the dripping faucet will drop the water at a constant rate, right? Although I think it's not mentioned in the problem here, but just by assumption, we know the dripping rate should be constant. So in this case, we can see that for this drops here, basically, if we assume that drop hits the sink in t seconds. Let's just use the seconds. You will see the unit doesn't matter in the seconds, but yeah, t seconds. Okay, so if the drop hits the sink in t seconds, then what do we know about this guy here? The drop in the air. So because there will be one drop is about to leave the sink, right? So we know for this guy here, he should take only t/2 of the time to travel this far, right? Does that make sense? Because think about this. For this time here, it's going to be a t, but right in between here, there's another drop, which emphasizes that like the drop will be released every t/2 seconds. Okay, so this will be what we can get out from this graph here. Oops. Let me bring this up here. Okay, and then we just wonder how far the drop is going to travel in this t/2 hours. So in this case here, it will be great if we can just use the above kinematic equations, right? So in this case, we are going to use this guy here, the last equation. So if we think about the displacement, for the displacement, if we see this drop here, right, the first one, the delta x is going to be the v0 multiplied by t plus 1/2 times the at squared. So in this case, you don't even need to know what a is. All right, we are going to worry about that in a second. And now we know that it's going to be 10 centimeters is equal to 1/2 a multiplied by t squared. The reason is because the v0 is actually equal to 0. This guy is equal to 0 because at first the speed of this drop is just going to be 0, right? Right before it's released, so it's going to be 0. But then if we think about the second case, see if we can bring another one here, right? If we think about the second case, we are going to think about what's going to be the displacement in only t/2 seconds. So we still have the v0 times, in this case, it will be t/2 because we only spend half of the time. And then we add 1/2 times the a t/2 squared. Okay, so everything about the time will be halved. And then this delta x is going to be, the first one is still equal to 0, but the other one is going to be a 1/2 times the a multiplied by a t squared over 4. So it's actually going to be a 1/4 times the 1/2 a t squared. So you can see that the distance it's going to travel in half of the time it will be just a quarter of the original displacement, and that's going to be a 1/4 multiplied by a 10 equals 2.5. So now we know that in half of the time, the drop is going to travel 2.5 centimeters. And the problem is asking what height above the sink. So we are looking for the height above the sink here, which will be 7.5 centimeters. So if we look at the problems here, for 7.5 is going to be the answer choice D, between 6 and 8. Alright, so that will be it on the first two problems here, and these two problems could be the simplest problem from the FE course MA, but you kind of got the sense how easy the problems could be from the test. Alright, so see you tomorrow here, and make sure you do the practice throughout the days.